now there is a little bit more light on the sun, but I hope everything will be seen nice. Okay. I just want to show properly the example that I forgot to how to do it was in the last lecture. So I had something like that. I wanted to show that we have a manifold with boundary for the disk, and I just want to say that around each point, so I have a point, and let's take maybe not that point here will work as well. And I want to take some parameterization. So here is the center. What I do is I will cut a disk from here, and I will consider this thing here. So this will be my V was there. So I say V I just define V from U. So I define U to be from 1/2 open to 1 closed times, and let's say some angle. Let's say from minus P over, I don't know, 6 to P over 6. And then V, I define F of R phi to be R cosine phi sin phi. And I'll define V to be the image of F. So, so this is the set of points R cosine phi sin phi, where R is from 1/2 to 1. So here is open, here is closed, and phi is from minus over 6 to P over 6. So that way, this thing here is like a square, a rectangle with only one boundary closed. Okay. Next, so this is from the first part of previous lecture. Now I needed to do exterior derivative in 3 dimensions. So let's continue with example. This is not writing very well. Oh, is this clear? Yeah, okay, much better than previous time. Exterior derivative on m equals R3. Okay. So instead of doing all the computations for each term, let me do how they're done for monomials, to say. So first, of course, df is df dx times dx, so partial x dx, and the same for the other 2 parameters. Of course, in general, I write x1, x2, x3, but in 3 dimensions, I can write x, y, z. Okay, this is like gradient. So the coefficients are like the coefficients of the gradient. And if you do the gradient, you will not have dx, but ddx. You had vector fields, not a form. So this is d0. Now let's do d1 only of dx. Only of dx. So this is d0 f wedge dx plus d plus f with d dx. And this is 0. So we only have the first part, which is this thing here. So this is df dx dx plus df dy dy plus df dz dz, everything which dx. Now dx y gx is 0, so I have only dy and dz, and I will group them. So I'll have df dz times dz wedge dx, and this I get with my sign minus. This will be df dy dx wedge dy, and this doesn't write well as well. I will erase this on the top. That just way makes a picture. No, it doesn't work. Let me try another one. Yeah, thank you. You want to put me? So this is for a single nut. Now if you do for 3 of them, so this is only if you have dx coefficient. If you have everything, dfx dx plus fy dy plus fz dz, this would be in a similar. So we did the first one. So this is df dz dz dx minus df dy dx wedge dy. And a similar computation can be done for other things. So I'll just add the results. I don't remember them, but I will just change variables. So this will be, so this is dfx here. This will be dfy over the x, and this will be dx wedge dy minus dfy dz, and this will be dy wedge dz. And for z term, will be df dz over dy. I'm just doing cyclic combinations, cyclic permutations. The y wedge the z minus df z the x the z wedge the x. And if I combine everything, so first I will get dx dy, so I get dfy dx minus dfx dy dy, sorry, not in this solver. I want dy dz to be the first one. So I have df z dy minus df y dz dy wedge dz plus df. Now I have dz wedge dx. So I have dz wedge dx. So So I have this, the fx dz minus the fz dx dz which dx plus have dx dy here df y dx minus the fx dy dz dx which dy. Okay, and these coefficients are like the coefficients of the curve operator. So this is like with when you have metric, it's more precise way. This is like curve of fx ddx plus fy ddy plus fz dz, and we have d dx is identified with dy dz, d dz is identified with dx which dy. So in vector calculus, we start with a vector field and return a vector field, but here in the exterior calculus, we differentiate between one forms and two forms. They are different objects with different physical meaning, which we'll see next time. Is everything right with the audio? Okay. And now let's do for two, or just first fix. So this was maybe one. This is D2 in R3. So first fix a simple monomial. So for monomial, d of d2 of f x, for example, dy dz is d of x wedge dy dz plus we have then d of we have f times d of dy dz wedge dz. This is the Leibniz rule. So we have brackets here like, and the first is, okay, I'll just do the first. So let me just don't write any equation. Let's first calculate this. So d of dy dz, this is d dy wedge dz minus, because we have one form here with the graded Leibniz rule, this is d dy wedge dz minus, because we have one form here with the graded Leibniz rule, we have minus sign. If you recall the definition, we have minus dy wedge d dz, and this is 0, and this is 0. So the whole result is 0. So anytime you make a differential of something involving only differentials, the result is 0. And so d of f, so this underscore here just says where we apply. We can omit it, it doesn't matter. So the operator d is the sum of all operators d0, d1, d2. Sometimes I write the operator, sometimes the indices, sometimes I don't. But in any case, this means that this is equal to the fx wedge dy wedge dz. And now let's expand. So the fx was the fx dx times dx plus the fx partial derivative with respect to y times dy plus partial derivative with respect to dy dz, sorry, dz, sorry, dz, and everything which dy which dz. Okay. Now, can you tell me what's left? What is cancelled? Not under. Not. Not. I said not under. Okay, we have dy here and dy here, so it cancels. We have dz and dz, so it cancels. So we only have the fx with dx, which dy, which dz. Okay, so similarly, we have the following. D of f y dz which dx is dy, so we have dfy dy, dy which dz which dx. And we have to make two changes, so we have to do this, go here and go here, and we have two sign changes, so the result will be dfy dy dx which dy which dz, and also d of fz dx which dy. Sorry, no, not two changes. I mean, in the opposite direction. So x goes here and then goes here. Yeah, this is dz. Now here we will have df z dz and dz wedge dx wedge dy. And this time we'll have movement here and also here. So two movements, and this will be df z dz. So maybe -1 to the second power, and here as well -1 to the second power. Dx wedge dy wedge dz. And so the whole result, yes, so d of d2 of x dy wedge dz plus fy dz wedge dx plus fz dx wedge dy equals to dfx dx plus dfy dy plus dfz dz, all of them multiplied by this three form. And this is like divergence. This is divergence of fx ddx plus fy ddy plus fz ddz. So we see that an operator given by just some rules in fact encompasses all the operators you know from vector calculus. In 2D it was gradient and scalar curve, and in 3D is gradient, curl, and divergence. So let me write that. So some summary of D in R2 and R3. So in R2 we'll have 1 point, let's say 0. No, this is 2. Like it's 2. 2.0. d0 is like gradient. And d1 is like scalar curl. And in R3, so again, d0 is like gradient. D1 is like curl, and D2, sorry, this is D1, and D2 is like divergence. And especially in, this can be made in diagram. So, for example, f of d1 to go to omega 2 of R2. And this will be like, here again, we start with R2. We have some identifications. Here is direct, but in another case, we will need some hot star, so I don't do that. Just show how they're related. So we have gradient, and we have vector field, and here we have, I don't know, scalar rotor, so scalar curl. No, the operator, how it's called, scalar curl, how we call scalar curl. And this is again here function. This is vector field, and here is a function. Function, sorry. Functions and zero four sound the same, but here we need some identifications with the metric. So we have some identifications here. And in 3D, so this is 2D, 3D, we have omega 0 R3, D0, omega 1 R3, omega 2 R3, omega 3 R3. So we have D1 and D2. And here we have functions, which is the same. Then we get vector fields. Again, vector fields and functions. Yes? This is grad, this is curl, and this is divergence. And so we have the following, because D1 composed with D0 is 0, is the same as curl of grad is 0. Curl composed with, and D2 composed with D1 is 0, is the same as curl, divergence of curl is 0. And you should know this from vector calculus. And this generalized, I mean, it can be done in 4 dimensions or in 8 dimensions, and it's much. These are operators, any of them defined in a different way. This is a single operator defined outright directly. Here, I don't know some identification. We have, I forgot, D1 to D0 is 0 is the same as scalar curl. I don't know how to call it. Composed with gradient is 0. We have identification to do, but it's more clear, not more clear, but maybe more illuminating in 3D. Because in 3D, especially the curve is defined with a very long formula, and here is defined by the rules. It can be derived from the rules for the exterior derivative. Okay. Where is my? Okay. Yeah. So this property that it's as called this cochain complex, that the composition of two operators is zero, but we will not be interested in that for now. Now let me define what a pullback is. It's an important notion. So let F M and N be smooth manifolds, and B smooth manifolds, and F is a smooth map. So F is a infinitely differentiable map. So yes, so the pullback on one forms F on one forms is F star from, so it goes from M to N, but now it goes in the opposite direction. So it goes from omega 1N to omega 1M, is defined by as follows. F star of, so follows, let me do as follows. For omega in alarm form, x point. No, I need differential. So I didn't define differential. I do it a different way. If let's say omega equals h1 dy1 plus hn dyn, then n is the dimension of n, then f star omega is h1. Oh, sorry, and here h1 to hn are smooth functions. They are from n to r. This is the set of algebra smooth functions, f of n, sorry. Then f star omega, so then is h1 composed with omega, with f times the y1. I don't know why I'm using upper indices. Doesn't matter. I will not be very careful about that. The y1. Let me just use lower indices everywhere because it just makes things more confusing. So this is the formula here. Hn composed with f, dy n composed with f. And before giving example, because this is a linear map, it can be expanded to forms and tensors. So f star, it can be extended to exterior, to tensor powers and exterior powers and exterior powers. Tensor powers, symmetric, Okay, exterior powers. Maybe symmetric powers. I didn't talk about that, but it can be. So first, let me do an example for a one form, and then for high-dimensional forms. Example. Okay, only one example. So let M and N are, let's say, no, M is R squared.
Sorry, were M and N both N manifolds?
No, only N.
Only N.
Yes, M can be arbitrary. Yeah. N is only the dimension of N, not of N. So M is R squared and N is or the other direction. M is R and then R squared. I'll just give the formula and then we'll see what's the proper. So F of R5. Yes, so they're both R squared. And I'll give the polar map. R cosine phi, R sine phi. I think from now on are in the preprint in archive. Everything before was not in the preprint because it will become 100 pages if I include that. But from now on, it will be in the preprint in some form. So F omega is, we'll see how this form comes into this, minus y dx plus x dy. Now, F star, maybe this example was not there. Doesn't matter. F star of omega is, so this is some kind of, so this is omega, so this is minus 1 composed with F, d of x composed with F plus x composed F, d of y composed with F, something like that. So let's apply this to R phi, so F star omega of R phi. So y is the y coordinate, so this will be minus R sine phi d of the first component, x is the first component, R cosine phi, plus R cosine phi d of R sine phi. And we P this, and here we have this is cosine phi dr minus r sine phi d phi minus r sine phi d phi. So we are doing with respect to r and with respect to phi. So the derivative with respect to r is cosine phi multiplied by dr, and the derivative with respect to phi is minus r sine phi, and then multiplied by phi plus r cosine phi. And here we have the similar thing. So we have sine phi dr minus plus r cosine phi d phi. Now we're expanding. So we got before dr we have minus r sine phi dr minus r sine phi cosine phi, and then plus r cosine phi sine phi dr plus, so we have two minuses, so r sine phi square sine squared phi, and then we have r cosine square phi, r cosine square phi df, and this is r times df d phi, sorry. We have r squared, yes. Yes. Okay. Or this is some, let me write as a theorem, I don't know, proposition, doesn't matter. So let me M and N be smooth manifolds. F is smooth function. So F is smooth function. And I said we can expand it. And F star P is from omega Pn to omega Pn. Here P is integer. Is the extension of F star to the exterior algebra. To the exterior algebra of omega 1 of exterior algebra forms, let's say. Yes. Then we have the following. So we have the following commutative diagram. So dp composed with, this is the derivative, the exterior derivative if in M of F star P is the same as F star P composed with exterior derivative in M. This is this here, omega Pn to omega. Here it is f plus 1. So we have f star. Here we have omega f p plus 1 star. And here we have d p m.
Should be M. Up there, says that. Up there,
Oh,
yeah.
yeah, I wrote them here, but yeah, sorry. Also, we have also, and but yeah, this is directly. Also, we have, but this is from the definition of exterior algebra. But let's type f star of omega wedge eta is f star omega wedge x star eta. This is purely for algebra. This is analytical theorem, so it depends on it's related to what we do with smooth manifolds, and this is pure algebra. This is the definition, in fact, of extension of a map. So this should be here. This is the definition of the extension. I did this in the algebra part of this course. Okay. Example. I have one. This is in the preprint. I will write it in a simpler way. So again, the same thing here, and f of r phi is r cosine phi, r sine phi. And now omega is dy dx wedge dy. This is a two form. And so we set f star dx is in fact d of x composed with f. Or maybe I don't use this theorem here, but it's an example of a two form. And this was d of r cosine phi, which is cosine phi dr minus r sine phi dr d phi, and f star dy is the y composed of f, which is the r sine phi, which is sine phi dr plus r cosine phi d phi, and f star of omega is f star dx wedge dy, which is f star dx wedge f star dy, and this is cosine phi dr minus r sine phi d phi wedge sine phi dr plus r cosine phi d phi. And now this with this is 0. We have only the second component. So we have r cosine phi cosine squared phi dr, which d phi minus this thing here, sine squared phi dr, which d phi minus this thing here, r sine squared phi d phi, which dr. But this change sign, and so the whole result be cosine squared cosine squared will be r dr, which d phi. And this is the Jacobian of the matrix of this map. And this is not by accident. So when you do f star on top dimensional forms here too, we get Jacobians in these guys in some sense. The trace. Another important thing which is related to integrating on boundaries. When you integrate on boundary, usually you multiply by some normals, like that. But in exterior calculus, or multiply with some tangent vectors if you are integrating on a curve. But in exterior calculus, you need the trace, which is again a general map in any dimension for any subdimensions and things like that. So let M be a smooth manifold and be a submanifold. So it's a submanifold. So a submanifold is subspace that is also a manifold. So N is also a manifold, smooth manifold. And iota from N to M be the embedding. The inclusion map. It's also embedding / inclusion. So because it's a subset, you can map anything, any type point to itself. So iota of x equals x for any x in M. So we have a subset and map to the superset. Any point stays the same. Then the trace, then the trace of N is, so trace N is by definition iota star of iota star. Trace N is by definition iota star of iota star. Let's call this N. Is the iota star of M. So this is a map from omega bullet M to omega bullet N. It acts on a restriction of forms and to boundary when N is a subset of the boundary of M, which is mostly what we will be interested in. So let's give example. So this is not anything new. This is just some. So this is not anything new. This is just some special case. A special case of pullback. It's called pullback because you go from one manifold to the other, and the pullbacks go in the other direction in some sense. So M equals R squared, and N is the one sphere. So we get so iota of xy, iota n of xy is xy for xy in S1. This is the definition. Now let's compute the trace of such a map. So trace of S1 is from omega bullet S1 to omega bullet R2. Okay. Now let's give some form. So choose some local coordinate. No, it's the other direction. So from R2 to S1. So
That's not the inclusion.
no, the inclusion map is here. So and the trace is in other direction. Now let's give example. Trace.
But then it should be a star there.
Oh, yeah, I forgot. Yes. So trace. I will omit the subscript. We have some function. If it's a two form and this is a one-dimensional map, it will go to nothing. It will become 0. The interesting case is a one form. So trace of, let's say, f dx plus y dy. And in polar coordinates, so x is r cosine phi. So trace is, by definition, it's something that stays here. You just map on the boundary with this formula. But when you try to represent it, you choose new local coordinates. So local coordinates for the circle are cosines and phis and sines. So x is cosine phi, y is sine phi. And so this is f of not r, f of cosine phi. So if we have fx and fy, ffx of cosine phi sine phi, ffx of cosine phi sine phi, plus d of cosine phi, plus fy, and then you d of sine phi. F of sorry. F of y times of applied cosine phi sine phi times d of sine phi. And this is some general function. So I just, and d of cosine phi is minus sine phi d phi. So this will be minus fx cosine phi sine phi times sine phi plus Fy cosine phi f of y at this point times sine phi, sorry, times cosine phi, all multiplied by d phi. Now, interesting cases that I gave before. So here fx and fy are smooth functions from R2 to R, which is the set of small functions of M. Okay. Now, if fx is minus y and f of y is x, we get, and omega is fx. So fx is minus y dx plus x dy. I used this example before. The trace of omega will have minus the second argument. So we have minus sine phi. So because this is y times, so this is times minus sine phi. Plus cosine phi. This is x argument is this, and this is the coefficient here, times this phi, which is equal to d phi. And the interpretation, some interpretation is the following: this vector field, but this is not this form, but if it's represented like a vector field, so if we have, so if I'm here 1, 0, I will point here. If I'm here, I will point in this direction. So no, x is, so this is the point 1, 0. So 1, 0. I just, so this is the point 1, 0. Then x, in the direction in
You get minus.
minus.
No, you get 2y. It goes up.
Minus y dx plus x dy. I just interpret this as minus y d dx plus x d dy. And then at the point 1, 0, the component of x should be 0 and the component of y. So x equals 1, y equals 0. So this should be here. Yes. And if I go here, this is x equals 0, y equals minus 1. If we go there, if I'm here, I will go there. And if I'm here, I will go there. And so we get some kind of circular motion. And when we restrict to a circle, so if I choose this circle here, for point, I will get the, here I get things like that, and things like that, and things like that. And I will get a circular motion. And this is like The form d phi is like d phi in some sense. And at any point, no, sorry, my interpretation may be not that right, but this vector field here minus y, or this form here, has this circular motion interpretation, but my computation of the trace maybe doesn't have that interpretation. So let me just finish here and I will think about that in a moment.